Exploring Life, Chapter 5. Chemistry of Carbon, Part 1. We're about to spend an entire lecture in this biology course focusing on just one element. You might be wondering, and rightfully so, what makes it so special? Out of all the elements in the universe, why does this one deserve so much attention? It's definitely not because it's abundant. In fact, when we look at the chemical composition of the universe, hydrogen makes up about 75%, helium around 24%, oxygen just 1%, and carbon, our focus today, exists only in trace amounts. So if carbon is only a trace element in the universe, maybe it's more common on Earth? Let's take a look. In Earth's atmosphere, nitrogen dominates at 78%, followed by oxygen at 21%. Still no sign of carbon in major quantities. Now, if we shift to Earth's solid crust, we see oxygen again at the top, making up 62%, followed by silicon at 22%, and aluminum at about 6.5%. Once again, carbon barely registers. Clearly, carbon isn't a major player in the universe or in Earth's overall composition. So why does it matter so much to life? That's exactly what we're about to uncover. Now here's where things get interesting. When we examine the chemical composition of living organisms, carbon finally steps into the spotlight. Oxygen makes up about 65% of our bodies, mostly because of all the water we contain. But carbon comes in strong at 18%. That's a massive leap from its trace presence in the universe and the Earth's crust. Hydrogen and nitrogen follow at 10% and 3%, respectively. Then we have a handful of other elements, like calcium, phosphorus, potassium, and sulfur, that collectively make up about 4%. And finally, trace elements like chromium, manganese, and zinc, present in tiny amounts, but still absolutely essential for life. It's almost like living organisms are carbon junkies, hoarding it, craving it, and disproportionately accumulating it wherever they can. These pie charts illustrate exactly what we just discussed. Each one represents a different environment: the universe, Earth's atmosphere, crust, ocean, and finally, living organisms. Carbon is shown in red. Do you see significant amounts of carbon outside of living organisms? Not really. So here's the big question. How did carbon, a rare element in the grand scheme of the cosmos, become the foundation of life? The answer lies in its extraordinary chemistry. So, why is carbon so important to life? Its atomic number is 6, meaning it has 6 protons and 6 electrons, 4 of which sit in its outer shell. And that outer shell is the key. With 4 valence electrons, carbon can form up to 4 strong covalent bonds. A simple example is methane, or CH4, one carbon atom bonded to 4 hydrogen atoms. But it's not just about bonding with other elements. Carbon can also bond with itself, creating long chains, branching structures, and even rings. From there, the possibilities expand dramatically. These carbon frameworks form hydrocarbons and complex molecular backbones. They also provide the foundation for attaching functional groups, chemical tags that fine-tune how molecules behave and interact. This remarkable flexibility is exactly what makes carbon so essential to life. Let's look at what carbon can build, starting with the simplest organic compounds, hydrocarbons. Hydrocarbons are made exclusively of carbon and hydrogen. What makes them special is that they serve as a kind of bridge between the non-living and living worlds. Methane, or CH4, is a prime example, the same molecule we just saw. These compounds can originate from volcanic eruptions, natural gas deposits, and biological sources. Methane is also a potent greenhouse gas, playing a significant role in regulating Earth's climate system. Along with other hydrocarbons, it serves as a starting point for much more complex molecules. What you need to keep in mind is that carbon chemistry is three-dimensional, and it can't be fully understood just by looking at flat, 2D drawings. On the left, the structural formula of methane shows one carbon atom bonded to 4 hydrogen atoms. It's helpful, but it only gives us a basic outline. On the right, the ball and stick model shows the molecule's true 3D shape. Each hydrogen atom is positioned about 109.5 degrees apart, forming a tetrahedral structure. And here's where it gets exciting. When these carbon building blocks start bonding with other carbon atoms, the possible shapes and structures become virtually endless. That's the beauty and the complexity of organic chemistry. Carbon atoms can form carbon skeletons. These are the basic frameworks of organic molecules, made up of chains of carbon atoms. These skeletons can be linear or branched, depending on how the carbon atoms are connected. Carbon can also form double bonds, where 2 pairs of electrons are shared between atoms, creating regions of rigidity in the structure. And beyond chains, carbon can form rings, closed-loop structures that serve as the backbone for many important biological molecules, including sugars and some hormones. Isomers are compounds that share the same chemical formula, but their atoms are arranged differently, often in three-dimensional space. And that small change in 3D arrangement can lead to big differences in how the molecule behaves, affecting its chemical reactivity, physical properties, and even its biological function. Here we see how carbon skeletons can take on different shapes. They can be linear, like in butane, or branched, like in isobutane. Some structures contain double bonds, as seen in butene and benzene, while others form rings, like the 6-carbon ring of benzene. What's fascinating is that butane and isobutane share the exact same chemical formula, C4H, but have different structures. That makes them isomers, and as we've just learned, even this small change in structure leads to different physical and chemical properties. Think of carbon atoms like Lego blocks. Here, we see 2 distinct shapes built from the exact same set of Lego pieces. Even though the pieces are identical, the way they're arranged creates completely different structures. Just like Legos, it's the carbon arrangement that matters. And that's how carbon serves as the foundation for an enormous variety of molecular compounds in living organisms. Now it's your turn. We've explored how carbon acts like a master builder, forming chains, branches, rings, and complex molecules, much like Lego blocks or connectors in a 3D puzzle. But how would you explain carbon's role in organic chemistry? There's a whole branch of chemistry dedicated entirely to carbon-containing compounds. It's called organic chemistry. It focuses on how carbon's composition, and more importantly, its arrangement, can lead to incredibly diverse chemical properties. What influences those properties? Things like molecular structure, branching, double bonds, and the specific atoms attached to the carbon backbone. It can get pretty complex, But at its core, these chemists are kind of like professional Lego builders, just with molecules. They explore how different combinations of the same basic pieces can create entirely new and useful structures. Organic compounds aren't made of carbon alone. They also include elements like hydrogen, oxygen, nitrogen, sulfur, and phosphorus. What gives these molecules their unique properties are functional groups, specific arrangements of atoms that influence how the molecule behaves. One key example is the phosphate group, which plays a major role in energy transfer. You'll hear about this group many times throughout the course. It's essential to how cells store and use energy. This table shows the structures of several key functional groups. The symbol R represents a generalized part of a molecule, a placeholder that allows us to focus on the functional group itself without showing the full structure. You've already heard about the phosphate group, which can act as an acid or base and plays a central role in energy transfer. Here are a few more important groups to remember, each with a distinct role. Hydroxyl increases water solubility. Sulfhydryl influences protein structure. Carboxyl adds acidity by releasing hydrogen ions. You'll encounter these groups often as we explore how molecules behave and interact in living systems. Functional groups aren't just chemical labels, they have real, biological impact. Even slight differences in functional groups can lead to dramatic physiological effects. A powerful example is testosterone and estrogen. These are the molecules of testosterone and estradiol. As you can see, they're quite complex. To make them easier to study, chemists often use simplified line drawings, where each vertex represents a carbon atom, and hydrogens and other atoms are usually left out. This allows us to focus on the overall structure and, most importantly, the functional groups. The difference between these two hormones comes down to just 3 functional groups, and yet, that tiny structural difference has a huge physiological impact. Testosterone shapes male characteristics, while estradiol drives female characteristics across many species, including humans. They truly represent the defining difference between yin and yang, no joke. Think of functional groups like specialized Lego pieces. The carbon skeleton is like the basic structure you build with standard blocks, straight pieces, connectors, and corners. But functional groups? They're the accessory pieces, hinges, wheels, lights, or moving parts. They don't just add decoration, they completely change what the structure can do. Many of the large biological molecules we'll study are macromolecules, or polymers, long chains built from repeating smaller units called monomers. These monomers are linked together through dehydration reactions. In this process, a bond forms between 2 carbon atoms, and a molecule of water is released. To break these polymers back down, the reverse reaction is used, hydrolysis. This reaction adds water to break the bond between monomers. These 2 processes, dehydration and hydrolysis, are central to how living organisms build and break down complex molecules. This illustration shows how monomers are linked and separated in living systems. During dehydration synthesis, a hydroxyl group from the growing polymer combines with a hydrogen from the incoming monomer. This forms a new covalent bond and releases a molecule of water. In contrast, during hydrolysis, that bond is broken, and a molecule of water is added. One part of the water attaches to one monomer, and the other part to the next, separating the 2 units. These two reactions are essential for building and breaking down the macromolecules of life. Think of polymers as a chain, and monomers as the individual links that make it up. When a polymer forms, it's like connecting one link to another. This process resembles snapping links together, and during dehydration synthesis, each time a link is added, a water molecule is released, almost like removing a protective cap so the pieces can bond. To break the chain, the reverse happens. Hydrolysis adds a water molecule, like putting the cap back on, causing the chain to split. This simple analogy helps illustrate how living organisms build and break down the complex molecules they rely on. We've laid all the groundwork, understanding carbon's unique bonding abilities, the role of functional groups, and how small molecular structures can make a big impact. Now it's time to see all of that in action. In Part 2, we'll explore how carbon forms the major biological macromolecules essential to life: carbohydrates, lipids, proteins, and nucleic acids.